Hi, everybody. It's Mr. Smith here with another video lesson for you guys. Today, we're going to optimize some trig functions, so find the max and min of some trig functions. To start off, we're going to do a bit of review because we've been, in our curve sketching and optimization from our last unit. We found a lot of extreme maximums and minimums, and that involved finding the derivative of a function and setting it to 0 and solving that resulting equation. So how do we do that with trig functions? How do we solve an equation that has some trig stuff in it? That's what we're going to do now. I've got 3 kind of like warm-up problems for us to do together, maybe review a few skills, give you guys the tools you need to to optimize some trig functions. So let's dive in. We're going to solve this equation here. 0 equals 2 times cosine theta plus 1. The thing with trig functions is because they're periodic, there would actually be infinitely many solutions to this if we didn't kind of restrict it to some domain for theta. So here we're going to restrict theta to be between 0 and pi radians. We might mix it up between radians and degrees when we can today, but 0 to pi radians is just from 0 to 180 degrees if you'd prefer to working in degrees, which would be okay with this particular problem. But let's talk about how we could solve this trig equation. Well, this one's pretty direct because you just have cos theta in terms of variables. It's very easy to isolate for cosine theta. So that's what we'll do. In this first question, we just solve for cosine theta. So taking 2 cos theta plus 1 equals 0. Sorry, I just rewrote the equation there. We can move over the 1. 2 cos theta equals -1, which means the cosine of theta equals -1 over 2. So we're looking for solutions between 0 and pi. Now, many of you guys, know all of your unit circle stuff. Some people just don't have it down as others. So do a little review now too. So in grade 11, you guys learned about the cast rule. You can take trig ratios of angles that are outside of a normal triangle, like past 0 and 180. And you guys learned the cast rule to just understand when a certain ratio will be positive or negative. So we know that cosine is negative. Well, cosine is positive in the C quadrant and the A quadrant for all. And it's negative in the sine quadrant and the tangent quadrant. So we know that between 0 and 360 or 0 and 2 pi radians, there'll be 2 solutions here and here. And for our particular problem, we're only looking for solutions between 0 and pi. So we just know that it's going to be the guy in quadrant 2 here between 90 and 180 degrees, or pi over 2 and pi radians. Typical starting point with a question like this, now that we've got cosine theta equals -1 over 2, at least for me, I just like to, let's just use our calculator and see what we get. This one, however, with cosine theta being 1/2, and this might be a good talking point, we can actually get an exact value in terms of radians, because this is one of the angles that corresponds to a special triangle. So I'm going to draw our 30, 60, 90 special triangle over here. Because this original question is in radians, instead of 60 degrees, I'm going to write pi over 3. Instead of 30, I'll write pi over 6. And if you recall this special triangle, we just divided an equilateral triangle in half, and we let the side lengths be 2, which would make the hypotenuse 2 there, which would make that leg 1. And then the root of 2 squared minus 1, that's the root of 3. This opposite side to pi over 3 would be 3. So in terms of what angle gives a cosine of 1/2, so that adjacent side would be, so 1 over 2, that's referring to pi over 3 here. So what we know is that the acute angle that this angle makes with the x-axis is pi over 3. So what angle is pi over 3 less than pi? Well, must be 2 pi over 3. So we've reasoned it out using special triangles in the cast rule that theta is equal to 2 pi over 3. At this point, I might take that and make it into a decimal and then just show that we can get that on our calculators. So 2 pi divided by 3 is about 2.1. And if your calculator is in radians mode and you did the inverse cosine of negative 1/2, you get the same value. You guys can't see my calculator. Maybe you can. There it is. Same exact thing. So, expectation is coming into this course is that you guys are familiar with radians and your special triangles, and we could reason that out precisely. But it's not the end of the world using our calculator. I just want to, for this particular one, I want to stress, like normally we would use the cast rule to find other solutions as well. Like we also know that theta equals, pi over 3 more than pi radians. So 4 pi over 3 gives you the same cosine as negative 1/2. However, that's outside our interval of 0 to pi. So it's outside our interval. And so we have just the one solution here. So 2 pi over 3 or about 2.1. So a bit of a long-winded example there for how direct it was, but we wanted to review a few concepts. I've graphed that function here. And you can see that we have only one between 0 and pi. There is only one solution, and it's between pi over 2 is about 1.7 and 3 pi over 4 is about 2.36. And so the value we got of 2.1 definitely seems to fit. And as usual, I'd recommend, it's not cheating to have a graphing program out. So I graph the function y equals 2x or 2 times cos x plus 1. And that's not cheating. It's actually really smart. You can kind of check your answers as you go. All right, so first one down, let's look at a different one. So here we have the equation 0 equals sine theta minus cosine theta. And we're going to solve this one on the interval from 0 to 2 pi. So this particular one won't work like A because, if I could rewrite this equation as sine theta equals cosine theta by rearranging and maybe isolating sine theta. I isolated cosine theta at the same time, I guess. But I just can't use my calculator as it is. I don't have the specific value for sine or for cosine. So we need something different. So this particular one is set up that we can actually turn this equation into an equation that only has one trig expression or trig ratio. We can do that by dividing both sides by the cosine of theta. And when we do that, we get the following. We get tan of theta using that quotient identity equals to 1. And now we can proceed just like we did in the previous question. So a couple good talking points here. Probably should know via your special triangles what angle gives you theta equal to 1. And so that's our 45, 45, 90 triangle. So I'll use pi over 4 or pi over 4 and 90. And to make this special triangle, we make a 45, 45, 90 triangle with legs of 1. And the Pythagorean theorem says that the hypotenuse would be the root of 1 squared plus 1 squared, so root 2. So the angle that gives a tan of 1 opposite of our hypotenuse is actually pi over 4. So if you use your calculator, it's going to give you pi over 4. So I'm going to say this. If you get pi over 4, that's what your calculator would give you, and that's what you get using special triangles as well. If you would just try that, make sure your calculator is in radians. Do inverse tan of 1. You get about 0.785, which does correspond exactly to pi over 4. So you can use your calculator. It won't give you the exact value. It'll give you the decimal. That's not the end of the world. But the cast rule, not the cast rule, special triangles can give you the exact values as well. Now, if this was like 1.17 or some kind of weird decimal like that, then you just have to use your calculator and get the best approximation you can. But here we can get the exact value. It's pi over 4. Now that's one solution. So a second solution we're going to get using the cast rule. So I'll get my pen tool back here. And we'll draw what we've seen, what we've got so far. So I'll just draw it maybe down here. Cast. So tan theta is positive 1. So tan is positive in the all quadrant and in the in the quadrant 3 down here. And so we've already got one solution, that's pi over 4. And the second solution will have the same related angle. It would be the angle that's pi over 4 degrees past pi. So I'm going to call that theta 1 for our first solution. And theta 2 would be pi over 4 past pi. So pi over 4, pi plus pi over 4, which is 5 pi over 4. And we got that solution using the cast rule. So we have our two solutions. That's the only two solutions between 0 and 2 pi. As decimals, just so we can check our answer, that's about 0.785 we said. And then 5 pi over 4 was about 3.93. And I have this guy sketched as well, right here. And so you can see between 0 and 2 pi, you do have two solutions, here and here. And if you do the math, I have my graph here with the intervals at pi over 2 intervals, and I've expressed them as multiples of pi. But you can check those. You can check those values and see that, yeah, they fit right in, and just check your answer. So it looks like we did pretty good. So that was our second way to solve a trig equation. Maybe you can divide by cosine or sine or manipulate the equation to get one trig ratio in it. Let's go on to our third one. So here's a trig equation, 2 times cos squared theta plus cos theta minus 1. And we're solving this equation on the interval from 0 to 180 degrees. We're going to work in degrees for this one. Because the entire equation is just in terms of cosine theta, there's no funny business. It's fine to work in degrees. However, later on, you might work with functions like the following, like x times sine x, or x plus cosine x. And then maybe in a week or so, we might do equations that combine exponential functions, like 2 to the power of minus x times cos x. And in that case, where we've got some non-trig expressions, we would have to use radians, something dimensionless. We wouldn't be able to use degrees. But for our particular problem here, using degrees is just fine. And when we do application problems, often, degrees is the most helpful in terms of like kind of trying to visualize a solution. So we're going to work in degrees with this one. So make sure your calculator is in degree mode when we get to doing some calculations. Let's talk about how to solve this guy. So if we think about our previous two methods, there's no way to get cosine theta by itself right now. Well, there is a way. I guess we could complete the square, but who likes doing that? That's kind of takes a while. And we can't just like do any clever manipulations to get rid of one of these cosines right now. So a good strategy here is to use substitution. So, and let me stress, this isn't the only way to do this one. As I said, you could complete the square with cosine theta. Even that is kind of similar to what we're doing. So like, we're gonna make this equation look a bit more familiar. The change of variables, we're gonna let u equal to cosine theta. And then what our equation becomes is 0 equals 2u squared plus u minus 1. And now that equation looks more familiar. We could solve, that's a quadratic equation. We could solve that by factoring or with the quadratic formula. This one I've cooked up. We can solve by factoring. So let's do that. Numbers that multiply to 2 times -1, -2, and add to 1. Those two numbers are 2 and -1. So we'll decompose the u. Common factor the first pair, so doing some group factoring, we get u plus 1. When we factor out -1 from the last two terms, we get u plus 1. That's good. And we get 2u minus 1 times u plus 1. So it looks like we're going to get two solutions for u here. So setting 2u minus 1 equal to 0, that would give a solution of u equals 1/2. And another solution of u equals minus 1/2. But we got to remember, and I'm just going to, I might squeeze this down here for now. U is equal to cos theta. If we plug back in what u is equal to, so we're looking for values of theta that give cosine theta equals 1/2 and cosine theta equals -1. So the question is, do you actually get anything meaningful from those? And if so, are they in our interval? So in this case, using special triangles or using your calculator, looking at cosine theta equals 1/2. You can use make sure you're in degree mode if you're using a calculator or use special triangles, but you can verify that you get 60 degrees exactly. Well, I didn't follow my own advice there. I've got my calculator in radians mode. I'm going to change that up in degrees. There we go. Shift cosine of 1/2. Yeah, it's exactly 60. Now, that's what our calculator gave us. If you want to just look at the cast rule, if you want for this one, but we're between 0 and 180. Cosine is positive here and here. So 60 degrees is actually our only solution we get from cosine theta equals 1/2. Because we're on the interval of 0 to 180. If it was 0 to 360, we'd have a second solution that's 60 degrees less than 360, so 300. But as it is, it's only our only solution from that is 60 degrees. But cosine theta could also be -1, and actually it is possible for the cosine of an angle to be -1. That's the lowest cosine gets, but it is possible. And in fact, your calculator or just using your unit circle, or you might just have this down already, but that gives 180 degrees exactly. And that is in our interval. So we actually have two solutions for this equation here. We got them by doing a clever substitution and then solving the quadratic equation and then plugging back in using the cast rule, kind of normal things. I have this graphed as well. I've graphed 2 times the cosine of x squared plus the cosine of x minus 1. And you can see that, and I have my axis here, I put it in degrees. So you can see we get our solution at 180 degrees and at 60 degrees. Yeah, those three equations we solved. Hopefully it's a little bit of a brush up on those tools, reviewing the cast rule a little bit of unit circle and radians. Hopefully you did some of that prerequisite work I posted a while back. But if you need help with any of that, of course, you can just let me know. But now that we've reviewed those skills, we're kind of ready to go into solving a practical optimization problem. So let's look at this one. So everybody, if you live in a home or apartment building, buildings have eaves troughs. Those are there to kind of let the water collect and run off into a desired spot. So it's not just running off our roof and sheets and getting into our basements and everything. Now, thing with an eaves trough is that because it's designed for the water to kind of flow through in a really heavy storm, you might have lots of water flowing through this eaves trough. And to make sure it doesn't get back up and overflow, you would like this eaves trough to have, the largest cross-sectional area possible. So we're making an eaves trough from some sheet metal. So what we're going to do is, here's this 20 centimeter long piece of sheet metal, and we're going to make a fold in the middle, and then this gets bolted to the wall. So at 10 centimeters, it's going to be bolted to the wall. And then the bottom of our eaves trough is going to be 4 centimeters long. And we're going to make another fold with the final 6 centimeters. And then the question is, what angle should we make this fold at to make this cross-sectional area of our eaves trough as big as possible so the most water can flow through it? So it's a very practical question. So, obviously, you can jot this down if you want to, but obviously for the domain for this one, the lowest the angle could be is 0. Like that would be the case of the diagram here. But that would make a pretty silly eaves trough. The area would be 0, the water would just run off. So that's kind of pretty stupid. You could also rotate the eaves trough like all the way past 90 if you want. Now, hopefully we'd all agree that when you actually get past 90, clearly the area of the eaves trough is a lot less. So what we're kind of looking for is there an angle between 0 and 90 that is going to give us the best area possible? So, intuitively, you might think maybe it's 45 degrees, maybe it's 60 degrees. Like right now, we don't really know. So let's dive in and find out. So we're going to apply the algorithm that we've had from earlier optimization problems. The first thing we need to do is we need to, for maximizing area, we need to determine a function for the area of this eaves trough in terms of theta so that we can apply the stuff we've been doing today. So we need a few things. One is that you need the area of a trapezoid. The area of a trapezoid, you take the top and bottom sides. So it depends on like where you learned this in grade 9. But in the Ontario curriculum, we usually use A and B for the top and bottom side, and then you average that and you multiply by the height of the trapezoid. So we need expressions for that stuff here. So I'm just going to switch colors. So let's derive an area formula. So the 4 centimeter side, that can be let's say that's my A in my formula. Now I need expressions for B and H. So those aren't too hard to find. So if I make a little right angle triangle here with the 6 centimeter piece, the height of this triangle, it's the opposite side to theta. So you can use the sine ratio. Sine is opposite over hypotenuse to reason out that the height here is equal to 6 times sine theta. People who have taken physics, you'll be really used to breaking things into components, but maybe just down below, I'll just quickly show that work. The sine of theta would be that height over 6, and then rearranging for the height, it'd be getting into the bottom there, 6 times sine theta. So that's where that came from. And in a similar way, you can show that this horizontal length is 6 cosine theta, which means we're pretty much done. The height is 6 sine theta. And then the longer side of this trapezoid, the top side, would be the bottom side, 4, plus this extra length, 6 cos theta. So we now have everything we need to find an expression for the area. So let's do it. So the area of this trapezoid eaves trough, sorry, my kids are stomping around up there. So let's plug what we know in. So we said that the bottom side was 4. The top side is 4 plus 6 cos theta. So that's adding the top and bottom, all divided by 2. And then the height is 6 sine theta. So everything there in terms of theta. So we're ready to go to take the derivative and solve. But we might want to clean that up a little bit. So in the brackets there, that's 8 plus 6 cosine theta If I'll divide that 6 by 2, that's 3 sine theta. And if I expand that out, I get 24 times sine theta plus 18 times cosine theta sine theta. Now, some of you guys might recognize 18 cos theta sine theta. You could use an identity and write that as 9 sine 2 theta. That wouldn't actually help us make the solving our setting derivative equal to 0 and solving any quicker. So I'm going to suggest just leaving it as that for the moment. And let's move on. I've got another slide ready to keep on with this problem here. So let's set the derivative equal to 0. So where's my cursor there? So we have a of theta equals 2. Just going to quickly jump back, make sure I have it right. 24 sine theta and plus 18 cos theta sine theta. All right, so maybe if you want to like pause the video and try finding the derivative on your own, you guys have all the tools. You can unpause when you're ready, or you can follow along with me right now. So let's find the derivative, a prime at theta. So the first bit's not bad, just the derivative of 24 sine theta is 24 cos theta. And then we have to use the product rule for the last bit. So I can just leave the 18 out of it. And so the derivative of cosine theta sine theta, product rule, the derivative of cosine theta is minus sine theta times sine theta, plus leave the cosine theta alone. Derivative of sine theta is cosine theta. And if I clean that up, expand it out, I get 24 cosine theta minus 18 sine theta cos theta. Excuse me, that's minus 18 sine squared theta plus 18 cosine squared theta. So at this point, some of you may be saying, well, I have sine squared theta plus cos squared theta. I can just make that one. You don't exactly. You have cos squared theta and minus sine squared theta. They do not, so we can't simplify that way. So our goal is to set this equal to 0 and solve. And if we think about the strategies we have that we learned earlier, there's no easy way to solve for any of these by itself. And there's right now we have cosine theta and sine theta. We could do a substitution like part C, but it's not quite ready for us to do that because we have sine squared theta and cos squared theta. So we are going to make use of the Pythagorean identity, but maybe not in the way you thought. We're going to use it to get this entire equation just in terms of cosine. So we're going to replace sine squared theta with what it's equivalent to, because sine squared theta plus cos squared theta equals 1. Sine squared theta equals 1 minus cosine squared theta. All right, and we can now clean that up. So usually when I do this problem with people, like it's, there is quite a lot going on with this question. There's a lot of steps, but every little step is manageable. We can do it. And finally, I might write the cos squared theta terms first. So 36 cosine squared theta plus 24 cosine theta minus 18. All right. Just double checking there. Looks like we're good to go. All right. So at this point, you guys can use the skills from that we learned, we reviewed together earlier on. We are now going to solve that equation. So we're going to let u equal to cosine theta, and that becomes 36u squared plus 24u minus 18. So what I'd like you guys to do is maybe pause the video, solve that equation. You might have to use the quadratic formula. get a couple values for u, replace u with cosine theta, and see what kind of solutions you get. Remember, and you'll use your calculator, make sure it's in degree mode. Remember, we're looking for solutions between 0 and 90. So there'll only be one from our calculator. We don't really need to use the cast rule at all. Yeah, if you want to pause the video and give that a go, or you can follow along with me here. So the equation we have is 0 equals 36u squared. Just going to double check, plus 24u minus 18. Set up the quadratic formula here. So u would equal negative 24 plus or minus the root of. So I'm just going to do this quickly. 24 squared minus 4 times 36 times 18 times negative 18. 4 times 36 times 18 be the root of 3,168 all over 2 times a, which is 72. So we're going to get two solutions. Let's see what comes out. So negative 24 plus the root of, and if you did this yourself, you can just fast forward through the boring stuff of me doing calculations too. Divided by 72. So I got, for this first part, I'll keep 4 decimal places here, 0.4484. And then might as well finish this off. Remember, u is equal to cosine theta. So that's going to give us actually a meaningful answer. You know, cosine can be between 0 and 1. And if you do inverse cosine for that, you get about 63 point, you know, depending on how accurate it would be, 63.36 degrees, which fits into our domain. Let's see if we get other answers as well. So a second solution with the quadratic formula, 3168 divided by 72. So you get u is equal to negative 1. I'll keep 4 decimal places, 1151, which means cosine theta equals negative 1.1151. But cosine theta is always between 1 and negative 1. So actually, this guy, even if you try your calculator, you're going to get no solutions. So there are no solutions from there. And we've actually got what we need to make the biggest area possible. Your angle needs to be 63.36 degrees. So if on your lesson sheet you want to write a concluding statement, I'll just, I'm writing on a tablet here, so I won't make this too wordy. You get the max area when theta is equal to 63.36 degrees. You know, that's a really useful thing to know for people designing these eaves troughs. You know, it doesn't, with about 10 or 20 minutes of work, we now know how to build our eaves troughs to actually optimize the water flow. So people designing irrigation channels, designing anything that water is going to flow through, this is an interesting problem. So yeah, as I said, quite a lot there. I would argue every step is manageable, that you guys could do it. Let's talk about next steps for you guys. So on the Google Classroom, I've posted a practice sheet with a few optimization problems. I've asked you guys to solve some equations and use our algorithm for extreme values to find max and min. And I've also given you one more problem, kind of like the eaves trough question. Very similar, actually. It's just with a trapezoidal like irrigation channel. So it'll be very similar in the setup and execution. So give that practice a try. Solutions will be on the Google Classroom. As usual, I would love to help you. If you just send me an email or want to connect via Google Hangouts. All right, guys, signing off for now. Hope you guys have a great day. We'll see you soon.